Hi, my name's Hayden. I'm still unemployed, and this is day 9 of doing Leetcode every day until I get a job. Right now, this is day, like I said, day 9. This is Leetcode 2874, maximum value of an ordered triplet 2. Now, if you remember in day 8, the previous video I made, we actually solved maximum value of an ordered triplet 1. And these problems are the exact same, except that in the first version of this problem, it allowed for an O of n squared solution to pass, and the only difference that this one has now is that it only allows an O of n squared or O of n solution. And last time I solved for the O of n solution, and I don't want to do that again because that would be redundant. But what I will do is that my previous solution was O of n time and O of n space, but there is an O of n time and an O of 1 space. So this would get rid of all of our pre-processing. So just a little refresher of the problem. We want to return the maximum score or value of a triplet of indices I, j, and k, where I comes before j and j comes before k. And the value of a triplet is this little function right here, nums I minus nums j all times nums k. Okay, cool. Um, how are we going to solve this now? First, we're going to check how we solved it last time. Last time, we iterated along the array on J, and we found what the maximum elements were on either side of this J value. So in this case, the max left of J would be 16, the max right of J would be 20. So this would be 16 minus 18 times 20 is our answer. So would that be 160? And we found that with some pre-computation that we were able to do this in O of n time and O of n space, which is pretty good. But we want to change this now to O of 1, which means that we can't have these pre-computed maximum left and right arrays. So we have to ditch this kind of train of thinking. How are we going to do this? Well, let's just kind of experiment. I had to try a few different things first, but this is what I landed on. And I said instead of thinking about iterating over the array on J, let's try K. K seems pretty simple. It's just the right side of this equation, and it's not in the middle of two maximization problems. We just will have one maximization problem if we're iterating over K. So let's do that. We're going to iterate over this array on K. All right. Since we're iterating along on K, we want to find the optimal I's and J's to maximize nums I minus nums J for each K. Well, it's actually difficult and inefficient to find on the fly these I's and J's. Instead of figuring out where these I's and J's belong, as we go along the array, we're going to store a magical variable for now called maxdiff, which is going to contain the maximum difference possible and the optimal value of nums I minus nums j possible for each k element. So we're going to have a magical variable for now called maxdiff. Will this work if we have this maxdiff element? Well, it will work. Why is this going to work? Because we're always finding the optimal value of nums I minus nums j, and we're iterating along all possible k's, eventually we're going to find the maximum answer of the value of the triple indice. So that's the correctness of our algorithm, which is great to know. All right, how are we going to implement this maxdiff? Well, the first thing that we're going to need is actually we're going to need to keep track of the max I element, and we're going to need to keep track of the min j element. And then we're also going to need to keep track of the answer as we iterate along. Okay, let's go through a toy problem. We're going to start by initializing these. So max diff, we're just going to set to 0. Max I, 0. Min j, we're going to set this to infinity. So any value we see next is technically a minimum. And then ands, which is a 0. So we're going to start with these as our I, J, and K. The first thing that we do once we start iterating is that we're going to want to set the max I equal to the maximum of itself or the new I element. In this case, there is a new maximum. 0 is less than 10, so 10 is our new maximum. Okay, let's go to the J element. Is J less than infinity? I sure hope so. All right, then we have 10 and 6 as our max and mins. All right, what's the maximum difference between these? Well, 10 minus 6 is 4. 4 is greater than 0. That solves that. And then we get 4 here. Cool. And then we're going to store our answer. This is a running average. And because we are getting the optimal value left of this K, even though that this may be the wrong answer, and you can look ahead and be like, oh, there's 20. If this does end up being the best possible max diff, we will keep it in this max diff variable, and we will iterate all the way to K equals 20 here, and then do this max diff times 20. All right, good to note that. All right, so our current ands is going to be 4 times 16, which is 64. All right, cool. What's next? All right, we're going to move our elements, our indices over some values. Okay. What about 6, 16, and 8? Do we have a new max I? No. New min j? No. Is there a new maximum diff? No. Okay. Is there a new ands? And we do have to calculate this because we did keep our optimal value here, and this would be the same situation as if 20 was here. All right, is our answer better? Still 4 times 8. 4 times 8 is not greater than 4 times 16, unfortunately. Okay. Now we are going to iterate one more time, or we're going to iterate again, and let's look at our values. Okay. What is the maximum of 10 and 16? Well, it's 16. Our max value is 16. All right, what's the min of 6 and 8? Oh, well, it's 6, but wait a second. We notice that this I variable must come before j, but we're still treating this 6 behind it as the minimum element. And if we keep going through this, we're going to have our max diff as 10, which is incorrect. Okay, how are we going to solve that? Well, each time that we see a new max I, we're going to nullify the min j variable. This goes back to infinity when we see a new max I. And this ensures that the next min j that we see, like 8, is the one that we're going to be treating and finding the difference on. So in this case, our new min j is actually going to be 8. And our max diff is going to be 8. And now, if we try and solve for this, 4 times 8, 32, still not the answer. All right, we're going to go over one more time. And we're going to do 8, 4 is 8 our new max I. No, is 4 new min j. Yes. All right. 4 is a new min j. A max diff, 12. All right, and then what's our new answer? Oh, it's going to be 12 times 20. Okay, wow, this is much larger than 64. This is 240. 240. Okay, that's our answer. And let's look at the code real quick. It's very simple code. So, like I said, we have our 4 values here. we have our 4 values here, and technically it doesn't matter if you start with a 0 or not, because we'll just be doing this. But let's, for the sake of the example, let's just do this. And the reason I'm doing 10 to the 6 plus 1 is because the maximum possible element in nums is 10 to the 6. So this is that just basically means any number is technically less than 10 to the 6 plus 1. Okay, so we go through. I get my I, J's, and K's. Easy enough. And then I'm going to do my max check. If I encounter a new maximum I, I'm going to invalidate min J. I'm going to invalidate min J. And then I'm going to set a new max I. And then if nums J is less than min J, I'm going to set a new min J. Simple as that. And then I'm going to solve for the new cur diff, and I'm going to compare that to the max diff. And if for any reason, and if the cur diff is greater than or equal to the max diff, set our new max diff. And then we're going to solve for our answer. And this is just going to be the max diff times the nums of k. And that's the ends. And as you can see, just for clarification, this passes. All right. This was Leetcode. What was this? 2874, maximum value of an ordered triplet 2. And this was solved in O of n time and O of 1 space complexity.